All right, my math counts people, we are going to do an area stretch today. So problems focusing on area. Before we get to area, we really need to know quite a bit about right triangles. Most shapes, with triangles being the most basic polygon that we have, most shapes can be broken down into triangles. And so a lot of problems with solving area in MathCounts, it really breaks down to, can you make the shape into triangles and then solve it from there. So here we go with the right triangles. First thing that we need to know about right triangles is the Pythagorean theorem. So the Pythagorean theorem says that if we've got a right triangle, and then these are called the legs, A and B, and then the C is the longest side. It's always the side that's opposite the 90-degree angle. This is called the hypotenuse. So there's a formula for solving for these sides. If you know two sides, then the third side can be found in this equation. A squared plus B squared equals C squared. So let's say, for instance, that we knew that, let's say we knew that this side was 5. So that would be the B side. And let's say that we knew that this side C was 10. And if we wanted to find the third side, we would just say, okay, then that's A. So A squared plus 5 squared equals 10 squared. So we'd get A squared plus 25 equals 100. And then we'd subtract 25 from both sides, and we get A squared is equal to 75. Okay, now we're stuck with, I want to know what A is, but I have A squared here. Well, the opposite of squaring is square rooting. So I would take the square root of both sides, and I get A is equal to the square root of 75. So that's how long that side would be. Now on top of this, MathCounts does want you to reduce your radicals. Root 75 is not a reduced radical. We will cover that a little bit more in depth a little bit later. You don't need it for the stretch that we're going to do here. But for those of you who want to know how to do it, basically we need to get out our perfect squares inside of 75. 75 is 3 times 25. And 25 is a perfect square. So this A equals to 75. We can break down 75 into root 25 times root 3. And then the square root of 25 is 5. So A would actually be 5 root 3. So this just means 5 times root 3. That's what simplifying radicals means, is all we're trying to do is find any perfect square factors that are inside of 75. Factors means things that are multiplied. And then pull them out. So root 25 times root 3 is root 75. And then root 25 is just 5. So this is 5 times root 3. All right. Next, these are really useful, Pythagorean triples, and you'll find them all over the place, especially in MathCounts. These are the two most common triple, and what I mean by triple is these are integers that work in the Pythagorean theorem. Because if I take 3 squared plus 4 squared, it does equal 5 squared, because 9 plus 16 equals 25. So this would be a Pythagorean triple. It's where if we knew that this side was 3 and this side was 4, we wouldn't even need the Pythagorean theorem. We go, oh, that must be 5. Or if this side is 5 and this side is 4, we automatically go, oh, this side must be 3. So it's a quick way to solve some of these Pythagorean triangles. And then another one that works is 5, 12, 13, because 25 plus 144 equals 169. So that's a triple. Now the nice thing about the triples is they scale. So having a 3, 4, 5 triangle, if we blow that triangle up to an even bigger triangle, where this side is 6 and this side is 8, see I'm multiplying by 2, then that means that the hypotenuse would also multiply by 2. So 6, 8, 10 is just another form of the 3, 4, 5 triangle. And you can keep on doing that by multiplying each of the sides by some number. So if I had a 9, 12, then this side would be 15, because then it'd be a 9, 12, 15 triangle, which is a 3, 4, 5. This is just the base pattern to it. And if we just multiply two of the sides by some number, the third side will be multiplied by that number. Same thing with this one. If we've got a 5, 12, 13, another triple that we could make off of this base pattern is just multiplying all the sides by 2. So if I make a bigger triangle where this side is 10 and this side is 26, well, I've multiplied the 5 times 2 and the 13 times 2, so we can automatically say, oh, this side must be 24. So you'll see these two patterns quite a bit, but you'll also see them like multiplied by 2 or multiplied by 3 or something like that. So anytime you see a 3 and a 4 in the legs, automatically you got a 5. Or some other product of that. So 6 and 8, you know you'd have 10. 9 and 12, you know it'd be 15, and so on and so forth. All right, so that's a Pythagorean triple. These are your main triples that you need to know. There are other triples out there. There is an infinite number of triples. Some of the other ones you might run across, but probably not, would be 7, 24, 25. And 8, 15, 17. 64 plus 225, 289. Yeah. So that would be another triple that would work. All right, getting on to special right. All right, sorry, somebody came in my room. I'm kind of lost. I don't know what I was doing. Special right triangles, probably? Okay, special right triangles. Okay, there are certain situations where you will not be given two sides, because remember in the Pythagorean theorem, you're required to know two sides, and then you can plug it into the Pythagorean theorem and find the third side. Well, some situations occur where you're only given one side, but you know the angle measurements. So the first one is an isosceles right triangle. So it's isosceles because these two angles are the same. When these two angles are the same, these two sides become the same. So this is an isosceles right triangle, and it has a pattern to it. The pattern is, since these two sides are the same, the hypotenuse will always be whatever this side is times root 2. So let's say, for instance, that this side is 24. If that side is 24, and it's an isosceles right triangle, well, this side's A too, so this would be 24. And then the hypotenuse would be 24 times the square root of 2. If we knew that this side was 36 root 2, well, that means this side's 36 and this side's 36. So it's a nice pattern to know that if you have an isosceles right triangle, you can follow this pattern of these two legs are congruent, they're the same measurement, and then the hypotenuse is whatever these legs are times root 2. Now you do get to situations where you have to multiply radicals. So let's say that this side was 2 root 2. So if this side's 2 root 2 and this side is 2 root 2, well, this side would be 2 root 2 times root 2. Well, how do you multiply two radicals? Where you just do 2 times root 2 times root 2, so this would be 2 root 4. And we know that the square root of 4 is 2, so this is 2 times 2, 4. So this side would be 2 root 2, this side would be 2 root 2, this side would be 2 root 2 times root 2, which is 4 after we've worked it out. The other one is a 30, 60, 90 triangle. This is a really nice triangle to have because it's half of an equilateral triangle. So an equilateral triangle is where all the sides are the same. So it's half of an equilateral triangle. because this one would be 60 degrees here, and this would be 30 degrees up here. And this side would be B, because this side's B and this B. So these two sides together make 2B, and this would be 2B over here. So this is half of an equilateral triangle. Anyways, the pattern is B, B root 3, 2B. Okay, so the smallest side over here is B. That means that it's half of the hypotenuse. And then this side would be B root 3. So let's say that we knew that this side was 5. If this side were 5, this side would be 5 root 3. Because B is 5, so 5 root 3. And then this side would be 2 times 5, which would be 10. Let's say, for instance, that this side was 12. That's 2B. So if I divide by 2, B is 6. So this side would be 6, and this side would be 6 root 3. And that's the pattern to it. So all you have to know is one side and know the angle measurements, and then you can find the other sides to it. All right, so let's get into area of shapes now that we've seen right triangles. So triangle, most basic of the shape, would be 1/2 the base times the height. Whenever we measure base times height, the height has to be perpendicular to the base. We call this an altitude. So the height has to be perpendicular to the base when we measure it out. So you can't just use any side as the height. The height has to be the side that's perpendicular. If none of the sides are perpendicular, coffee, then you have to draw in your own height there. If you have a right triangle, then the legs are your base and your height. If you got a triangle that's not right, you have to have an altitude drawn in there to be your height. So it's always 1/2 of the base times height. And the reason is because in a right triangle, you could always make a square. And so it's half of the, or a rectangle, it's half of that. So squares are always the side squared. So in a square, all the sides are the same. So the side times side would be our area. Rectangle, you guys know this one, is base times height. And again, height always has to be perpendicular to the base. Trapezoid is 1/2 the base 1 times base 2. So in a trapezoid, this might be base 1 up here. This might be base 2 down here. Your height in it, again, heights are always perpendicular to the base. So you have to find a perpendicular line to one of your bases to find your height in there. So it'd be half of your height, and then it's basically taking the average of the two bases. Finally, a circle. Circle is pi r squared. When they give you the problem as a circle and they say, give me the answer in terms of pi, that means you don't use the rounded number of 3.14 for pi. Remember, pi goes forever. When they say give it in terms of pi, they want the exact answer, and you cannot write the number pi because it goes forever. So the only way to give an exact answer is to leave pi in there. So let's say that we knew that the radius was 3. So pi times a radius of 3, then the answer would be 9 pi. So that just means 9 times pi. Because the pi goes forever, we can't write the actual answer, so we use the symbol pi in there to show it. Now, if we wanted to round that answer, we'd just do 9 times pi, and then we would get 28.274, blah, blah, blah. It keeps going forever because we're multiplying by a number that goes forever, so we'd have to round that. But if you want the exact answer, we'd have to leave it as 9 pi. That's what it means when it says leave in terms of pi. Okay, now we have a sector area. Let's say that we've got this sector here, and we only want this part of the circle. So this is, let's say, a 90-degree angle right here, and I only want this part of the circle. Well, what you would say is, well, we only want a fraction of that circle. So a circle has 360 degrees in it, so we do something like 90 divided by 360, and then times pi r squared. So this would be 1/4, because 90 over 360 is 1/4. So times pi r squared. So this would just be 1/4 of the entire circle. And then if you had 60 degrees, it'd be like 1/6 of the circle or something like that. All right, so let's do a couple practice problems just to make sure that you guys understand what we're doing here. All right, first one. It's a right triangle. We've got 3 and 8. We want to find this side. So since we know 3 of the sides, then we can use the Pythagorean Theorem. A squared plus 3 squared equals 8 squared, because 8 is the hypotenuse. So we'd get a squared plus 9 equals 64. Then we'd subtract 69 from both sides. And we get a squared is equal to 55. Okay, how do we get a by itself when it's a squared? We take the square root from both sides. So the square root of a squared is a. And then over here, this is just 5 times 11. So there's no perfect squares inside of that. So we would just leave it as the square root of 55. Over here, this is a 45, 45, 90 triangle. So this is the pattern of a root 2. So since this side is A, and we know that it's an isosceles right triangle, then if this side is 9, this side would be 9, and this side would be 9 times root 2. Really quick way once we know the patterns. For this one, we are missing 2 sides, but we have a third side, and they gave us the angle measurements. That means this is the B root 3, and 2B side. So if 2b equals 10, b would equal 5. So this side would be 5, and this side would be 5 root 3, using the pattern of b root 3, 2b. Okay, over here, I know 2 sides, and I want to find the third side. So this is a Pythagorean Theorem problem. We do 3 squared plus 2 root 2 squared equals c squared. So 3 times 3 is 9. Now what's 2 root 2 squared? I'm going to square the 2 and I'm going to square the root 2. So 2 squared is 4. Now I already told you that square roots and squaring were opposite operations, like they undo each other, right? So anytime you square a square root, the square root just goes away. So the square root of 2 squared is 2. So this is 9 plus 8 equals c squared. 9 plus 8 is 17. And then we take the square root of both sides. So c would be the square root of 17. There's no perfect squares inside of 17, so that would be our answer there. All right, here we want to find the area of this one. All right, so we've got a height here. We've got a base. So this is 1/2 base of 18 times the height. But I don't know what the height is. This is not the height. But they've got an altitude here. They've got 90 degrees because that's an altitude. 45, 45. So what we have here is a 45, 45, 90 triangle. Remember, this is the a root 2 side. So if this is 10 root 2, this side is 10, and this side is 10 in the 45, 45, 90 pattern. So this would be 1/2 of 18 times 10. Half of 18 is 9, and 9 times 10 is 90. For this one, we want to find the sector area. Okay, so this is 90 degrees, so the sector would be all of this section here. So this would be 1/4 of the whole circle. And then we do times pi times 6 squared. So we're going to have 1/4. 6 squared is 36. Pi. So what's 1/4 of 36? Well, we divide by 4. And our final answer would be 9 pi for this sector area. So basically we're saying that this part, the whole circle, has 36 pi. But I only want 1/4 of the circle here. So that would be 36 pi divided by 4, which is 9 pi. Now, what segment would be if we just wanted this little section right here. Okay, I told you that in circles, you're going to see triangles. We're going to see triangles in a lot of our shapes, and there's a triangle here. Now, what we have to remember is that if this radius is 6, this radius is also 6. So that is an isosceles right triangle. So what I can do here is I can say, okay, if I want just this part, I would take the sector area and subtract out the triangle area. So this triangle right here has a base of 6 and a height of 6. I know these are the base and height because this is the 90-degree angle. So we already said that the sector area was 9 pi, and then I'm going to subtract 1/2 6 times 6. Base of 6, height of 6. So I get 9 pi minus half, minus half of 36, which would be 18. And I would leave my answer like this. Why? Because these are not like terms. This says I have 9 pi's, and this says I have minus 18. This is not 18 pi's, it's just 18. So I can't take away 18 from pi's, because I'm keeping track of how many pi's I have here. So not like terms, so we would just leave our answer like that. 9 pi minus 18 would be the area of this section. Now we could find out how much that is by doing 9 times pi and multiplying and getting a number. But remember, it's not going to be an exact number. We'd have to round at some point. So this is the exact answer. If we wanted to round to the nearest whole number or something like that, I could just multiply 9 times pi in my calculator. It'd give me an approximation, and I can subtract 18 from it. All right, that's all I got for you today. Enjoy the area stretch. The last couple problems are crazy, but if you can persevere through them, you will learn quite a bit. All right, thanks, guys. See you later. Bye.